All right, so today we're just going to finish up with algorithms and algorithm analysis. And we left off last time by looking at binary search. And rather than repeating, writing it down, come on, there we go. I just brought in the pseudocode from the Computer Science 1 textbook, which is basically what we reproduced here. All right, you've got these two indices. This is the recursive version. So if you've got these two indices that start at 1 and n, eventually you're coming in on each other. The second that they pass, then you output phi because it was an unsuccessful search. Otherwise, what you do is you compute the middle index. You're given L and R, so you just simply take the average to jump to that index. And if that's the thing that you're looking for, if the element in the middle is equal to the key that you're searching for, then you got lucky and you stop with the successful search. Otherwise, if the thing that you're searching for is greater than the middle element, then you need to search in the right list, which means that you're updating your, so that's your elementary operation in practice, okay? So what we need to do is we need to analyze this. And when you analyze a recursive algorithm, there's not a nice clean way where you can set up a for loop and then come up with a summation and then solve that summation in some closed form solution. So instead, what you need to do is you need to define a function that captures the elementary operation. So to do that, I'm going to come back and forth here. One, I'm going to define C sub n. Right? And why C sub n? Well, C is going to stand for comparisons. It's going to be the number of comparisons made by binary search on an array of size n. So I'm taking the input size as input to my function. Remember, that was what we were trying to do anyway. T sub n, what is the time taken on an input size of n? What are the number of comparisons taken by this algorithm on? Two, we need to define, define the function as a recurrence. Right? That means that the function itself is going to depend on itself. It's going to refer back to itself. Okay? And then finally, three, solve it. Right? Okay? And that's the kind of the step that we're going to skip because we're going to use a nice little tool to do it for us. So let's come back over here to the pseudocode here, and let's start reasoning about these comparisons right here and right here. First of all, the base condition. If I have an array of size 0, then what takes over here? The base condition. Do you make any comparisons here on lines 1 through 3? Nope. So how many comparisons do you make does binary search make on an input size of 0? 0. That's our base condition for the recurrence. A recurrence is kind of like the Fibonacci sequence, where the next value is dependent on the previous values in the sequence, right? And where you got to start somewhere. Where do you start in the Fibonacci sequence? 1 and 1, 2, 3, 5, dot, 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 dot. And so what we need is we need a base condition for our recurrence here, and that we're going to eventually come up with. Okay. Otherwise, how many comparisons do we make? Well, we've already reasoned that there's 1, 2, but then we kind of conveniently, without loss of generality, collapse those back into 1, right? 1 for each recursive call. Okay? So is the answer 1? Do I call binary search once and then end there? No. Binary search calls itself. And it calls itself again, depending on whether or not you want to search in the upper half or in the lower half. Okay? So, do we have a function that tells us how many comparisons binary search, a recursive call, to binary search makes? Yes, that was the purpose in defining this function. C sub n is going to be the number of comparisons made by binary search on an array of size n. So look at this one in particular. What's the input size when I make that recursive call? Remember the idea. You've got L and R. And the middle guy was not what you were looking for. Otherwise, that would be taken. So we recurse on the left or we recurse on the right. If we recurse on the left, which would be what? This one. Right? How big is the new array size that we pass to that recursion? Half, roughly half. So yes, -1 because we no longer look at that middle element there. So n minus 1 divided by 2. I don't want to have to worry about constants. So let's just go ahead and say that the size here ends up being n divided by 2. Right? Likewise, the size here ends up being n divided by 2. Do both of those recursive calls get made? Nope. Else if else. They are mutually exclusive. So either this one gets called or this one gets called. We might get lucky here and say, stop, right? Imagine that if that happened on the first iteration. We called binary search and we immediately found that element right in the middle. The element right in the middle of a sorted set or a sorted list is what? We call that thing the median, right? So we were searching for the median. We got lucky and we stopped. Can we always assume the best case scenario? Nope. No, no way. Right? Yeah, go ahead.
Are we still talking about an array size of 0?
Nope, that's the base case. Right? We're setting up this recurrence. Okay. So there's one comparison for each recursive call plus the number of comparisons in a recursive call on an array of size, we already identified it, n divided by 2. Right? So now let's bring all of this together over here. Part 2, define the function as a recurrence. C sub n is equal to 1 call to binary search on an input size roughly 1/2 of the original, plus 1 comparison in order to determine do you need to go to the left, the right, or stop because you found what you were looking for. All right? Again, this is the cost of the recursion. How many comparisons are you going to make when you go down in the recursion? And this is the non-recursive cost. Okay? This is a recurrence because f, or the function, c, is defined in terms of itself, c, right? So you have to now solve this. 3, solve. I don't know if you've covered or you will cover recurrences in, say, 235. They're called difference functions. They're basically the discrete analog of differential equations. And you basically have this nice little step-by-step plug-and-chug process. That process really only works for linear, homogeneous recurrence relations and linear, non-homogeneous recurrence relations. Unfortunately, we don't have a linear homogeneous recurrence relation here. What we have here is a non-linear, non-homogeneous recurrence relation. Don't worry about it. Let's just go ahead and solve it. I'll show you how you can solve it. Okay? You solve it by unrolling it. Right? So what I need to do is I need to get rid of this thing. I just want a number, or a number involving n. What I can do is I can plug this back in over here. When I do, what do I get? If I plug in n divided by 2 into n, I get c sub n divided by 2, n divided by 2, or n divided by 2 divided by 2 again, which gives me n divided by 4, plus 1. Right? That's me expanding this one out. Don't lose the original 1 up there. Right? There's nothing to stop you from unrolling this again. If I plug this thing in over here, what do I get? I get n divided by 4 divided by 2, which is n divided by 8, plus 1. And that's me expanding this part out and including those ones that are still there. Dot, dot, dot. When do I stop? I stop at that base condition, c sub 1 equals 0. And then I make sure that how many ones have I added up to this point, okay? And you can come up with hopefully you see the pattern here. When you unroll these things, called back substitution sometimes, you start to see the pattern emerge. If I did this, I did this once, twice, thrice. If I did this I times, what would I end up with? C sub 2 to the I, right? Because divide by 2, divide by 2, divide by 2. You're taking powers of 2 in the denominator. Plus, and then how many ones would I have? I ones, right? Why? Because here it was the exponent was 2 to the 2, so I was 2, and I had 1, 2. Here it was 3, 1, 2, 3. Here it's I, so I. Right? When do I get down so that this disappears? Well, if I go too far, technically, can you divide by 2, divide by 2, divide by 2, and ever get to 0? Not technically, but this is discrete kind of math. So 1 divided by 2, floor, right, will get me 0, right? So eventually I get down to where this becomes, but for all intents and purposes, for what I get, basically makes this go away. What you can do is you can take a different subcase here. C sub 1 is equal to 1. If you want to solve this thing exactly, right? So when do I get down to c sub 1 is equal to 1? Or when do I get down that c sub n divided by 2 to the I is equal to c of 1? It's when n divided by 2 to the I is equal to 1. That's when n is equal to 2 to the I. It's when I is equal to log base 2 of n. So, dot, 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 c sub 1 plus, if that's my I, that gets plugged in over here. And guess what? 1 plus log n, that gives me order log n, ignoring that lower order term 1. Right? That's how you solve this. Let's look at a much easier tool to use. Right? Remember that we've got it of this form. C sub n is equal to C sub n divided by 2 plus 1. And again, the interpretation here is that you are doing a recursive call on an input size that has been decreased by some constant value, not constant value, but by some constant factor. You've divided it in half. And then you've got some function over here capturing the notion of non-recursive cost. If you have it in that form, you can use this thing called the master theorem. Now here it's using thetas everywhere. Don't worry about those thetas. Theta implies big O, so we'll keep it with big O. But let t sub n be a monotonically increasing function that satisfies this. Basically, it's a recurrence, but you are making a recursive calls. Right? You are taking the input n and you're decrementing it by some constant factor. If b was 2, like it is in our example here, that means it's half as big. B could be 3, and it's 1/3 as big. B could be 50, and it's 1/50th of what it originally was. Right? You just need to cut the input down because you need to get down to, say, this base case right here. And then there's also this function hanging off that is capturing the notion of non-recursive work. Based on the behavior of that function, one of 3 things will happen. It has to be bounded by a polynomial, n to the d. Right? And once it's bounded by a polynomial, that non-recursive function there has to be bounded. But otherwise, once you've identified A, the number of recursive calls, B, the factor by which you're decreasing the input size, and D, and then D, that's your bound on your non-recursive work. One of these 3 things will happen depending on one of these 3 conditions. This first one, this case 1, it's basically capturing the idea that you are doing fewer recursive calls, A, than you are doing non-recursive work. The second condition is basically saying that you are doing just as much recursive work as you're doing non-recursive work. And the last one here says that you're basically doing more work in the recursion than you are non-recursive work. Okay, that's the idea. And if this were 235H, I would go through a derivation of this. Basically, it's what I just did, but with A, B, and D defined. And then you come up with this big giant tree. Okay? But otherwise, let's come back over here and identify A, B, C, and D. Or A, B, and D. What is A? How many recursive calls are we making? 1. What is B? Clearly labeled. Again, it's, at this point, it's just plug and chug. 2. Except, what is our f of n? Our f of n is 1. How would you characterize that using big O analysis? 1. Which is, if I have n to the d, what would my d be then? D is 0. It's perfectly fine and valid to have 0 for d. Right? Over here, d is greater than or equal to 0. Right? So, set up my comparison here. A versus b to the d. Just plug and chug. 1 versus 2 to the 0. Less than, greater than, or equal? Equal. And by case 2 of the master theorem, I've got that it's this. So by case 2, I have that C sub n, the number of comparisons made by binary search on an array of size n, is going to be order n to the d log n. However, what did we just say that d was? 0. So what happens to this? Goes away. And we are left with log n. Exactly like when we solved it. But we didn't have to solve anything. We just had to plug and chug with the master theorem. It is a bit of a misnomer because it really only applies to recurrences of this form, right? If you've got a linear non-homogeneous recurrence relation, then you have to solve it using a variety of techniques. Pull out your differential equations math book and get rid of all the sines and cosines, and it's basically the same thing. Right? Okay, great. Let's get some more practice. Right? Let's remember how quicksort works. I'm not going to go over the pseudocode because you did that yesterday in your lab. You took the pseudocode and you transcribed that to actual code so that you implemented quicksort. Right? But let's walk through how that partitioning worked. Right? So 8, 3, 4, 1, 9, 1, 4, 10, 2. There we go. All right. So let's remember how quicksort works. The partitioning, that is. I choose a pivot element. Okay? And like a pivot foot, I'm putting everything that is less than it on the left partition. I'm putting everything that's greater than it on the right partition. And the way that the pseudocode did that in yesterday's lab is that you start out with these two indices, I and j. And on the left-hand side, you start incrementing I until you find something that's on the wrong side. Right? So 3, that's less than 8. It's already on the left. It's already on the left part, so we don't move it. We update I. 9 is greater than 8, so it's on the wrong side. It's on the left side. It needs to go to the right side. Once we've found something that needs to be swapped, we then switch over to j. 2, it's on the right side. It needs to be on the left side. So we've found our first two candidates that are on the wrong side. If these two things are on the wrong side, what do we end up doing? We swap them. Right. So 2 and 9. And we continue. I is now pointing to this one. J is now pointing to this one. 1 is on the correct side, so we increment. 4 is on the correct side, and we increment. And we find something that's on the wrong side, 10, from the perspective of I. Then we switch over to looking at J. But J and I are already pointing to the same thing. At that point, the partitioning stops. And if you looked at the pseudocode, hopefully pretty carefully, after that loop that did this, that brought I and J together, swap, 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 move, 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 it made a decision. Where does this pivot element need to be? Should it be here, or should it be one before? Right? And what it ended up doing, well, if I swapped 10 and 8, that would put 10 on the wrong side. So it went with the second case where, okay, then I'll go over here because I know that that's on the right side, the correct side, the left side, and so it's okay if I swap it with the pivot choice that I made of the first element. And so we end up with 4, oops, and what was there, 8? There. In either case, 8 is where it needs to be, right? And we've got a left part and a right part on which we recurse. Right? You do the same thing with the left part and the right part. This ends up becoming your new pivot. This ends up becoming your new pivot in that recursion. Okay? Yeah, go ahead.
Sort of don't understand some sort of things in terms of the I, or the I is one after the pivot.
Right. You start I at one after the pivot, J all the way at the end, and you move in until you meet in the middle. Swapping if they're on the wrong side, so that, and then finally when you're done, okay, the pivot needs to be here or here. In any,
I or J from,
swapping whatever I and J are referring to, yeah. Right. And there's a fuller example in the book. Okay. No, I don't have a pre-prepared video on that, but in any case. Now let's think about this in general. If I've got a pivot element here, how many comparisons does this partitioning work? Again, we're only taking a look at that partition subroutine, okay? Well, I starts at one end and J starts out at the other. And right now, let's just assume that there are n elements in here. I and J, you compare until you find something that needs to be swapped, and then you move along. Right? So and you're always comparing with the pivot element here. Right? So if you're comparing with a pivot element to everything else in this entire array, how many total comparisons do you make? N minus 1 because of the pivot element. So our first observation is that partitioning takes n minus 1 comparisons. And note that that's your non-recursive cost. I didn't have any recursion here at all yet, right? When you're done partitioning and you've got your pivot element, then you recurse on the left, then you recurse on the right, right? So that's your non-recursive cost. What about the recursion? We make, how many recursive calls do we make now? One for the left and one for the right. So we make 2 recursive calls. One for the left, one for the right. But here's the problem. Right? Was it an even split? In this particular example, there were 4 over here, and there were 2 over here. Right? So think about the worst case scenario, where all n minus 1 of them get shoved over here, or they all get shoved over there. And you have a partition that is empty, and a partition with n minus 1 elements in it. That's the unlucky situation. Tell me about that. What pivot choice did you make that ended up being like that? The largest element, or shoving them all on the other side, the minimum element, right? So worst case scenario, worst case. The partition ends with n minus 1 elements in 1 and 0 in the other. In that case, do we really need to make 2 recursive calls? Nope. Why would you make a recursive call? I mean, you could, but then you're not doing any work once you get there. Oh, thank you for this empty array. I'm not doing anything, return, right? So we're only making 1 recursive call. If I set up C sub n to be the number of comparisons made by quicksort in this worst case scenario here, then what do I have? I have 1 recursive call, in which case I won't even write it, on an input size of how big? N minus 1 elements. Plus, in order to do this, it required me to make n minus 1 comparisons. Oops. All right. Now, this is a linear non-homogeneous recurrence relation that you could probably solve using, say, 235 material. Or you could just kind of preview it, right? What if I were to unroll this one? What would it look like? If I plugged in n minus 1 over here, I would end up with, expanding this out into C sub n minus 2 plus n minus 2. That's when I would end up plugging n minus 1 into n. So n minus 1 ends up being n minus 2. And then don't lose the original. Okay? Do that again. What do you get? C sub n minus 3 plus n minus 3 plus n minus 2 plus n minus 1. Dot, dot, dot. Do you see the pattern emerge? N minus 1 plus n minus 2 plus n minus 3, dot, dot, dot. When I eventually get down to the end here, what will I have? 1, and then now work left to right. 1 plus 2 plus 3 plus 4 plus 5, all the way up to plus n minus 1. It's just the opposite of the summation that we're now familiar with. Are we still calling him that guy? That smart guy, right? By Gauss, we have that this is going to be order n squared. And it makes sense. If you always choose the minimum and put it here, and everything gets shoved over here, then you choose the next minimum. You put it here, and everything gets shoved over here. What does that sound like? Selection sort. That's exactly selection sort. Yeah?
We don't care about the minus 1, minus 2, minus 3, and so on. Or like
Asymptotically, no, but it'll end up being, in the end, if you use Gauss's formula, it'll be end up being like n times n minus 1 all over 2. The minuses contribute to that 2. So if you care about an exact solution, then you do care about those things. But if you don't, then yeah, you could overestimate each one of these to be n. How many of them are there going to be? N of them. N n's is n squared. Right? So we can't always assume the worst case scenario in this particular case. Which is more likely? That you're going to get super unlucky and always choose the minimum every single time? If you do, guess what? It's already sorted. Right? There are other worst case scenarios, right? You could always you could go with the minimum, then the next, then the maximum, then the minimum, then the maximum, min, max, min, max, min, max, right? And then you're shoving things over to one side on the left, then the right, then left, right, right. So there are lots of degenerate cases where you will end up with basically selection sort. But let's think about a better scenario, right? So the best or even average case, each partition is of equal size. And again, forget about the minus 1 because of and also forget about, odd-sized inputs, right? You can't divide 9 elements into 2 perfect partitions. So each partition will have n divided by 2 elements. Right? Now, how many recursive calls do we end up making? If there are n divided by 2 over here, and the pivot element goes right in the center, and there are n divided by 2 over here, I have to recurse on the left and recurse on the right. But they're both about equal, and so I'm left with C sub n divided by 2 for the left recurrence, C sub n divided by 2 for the right, and I still have to do my partitioning, so I'm left with that. Okay? And there's my C sub n for quicksort. The number of comparisons required for, or that quicksort makes in the best or the average case. Okay? Now, let's use our tool. You'll note that I'm just going to collapse these two because they're the same term. 2 recursive calls to quicksort on an input of size roughly 1/2, plus a linear amount of work in order to partition it to get it to that point. So, by the master theorem, let's identify A, B, C. A is 2 recursive calls. B is 2. And D is, well, n minus 1 is order what? N. So what's my D in that case? 1. A versus B to the D. 2 versus 2 to the first. They are equal. And so yet again, by case 2 of the master theorem, we have that C sub n is order n to the D, which is 1, so I won't write it, log base 2 of n. Right? It's a quasi-polynomial or quasi-linear sorting algorithm. It can go haywire, but only in very, very unlucky situations where you just happen to select an extremal element every single time. There are ways that you can mitigate that, by the way, by randomly, instead, like the one that we gave you for lab, always chose just the first element. You could randomly select an element out each time, right? And then random chance says that you won't always select the minimum. You could take 3 elements and then take the median of those, right? That's a constant amount of work, right? And you're guaranteed not to have at least n minus 2 over here and 1 is your worst case scenario. Except that, well, what's our ideal again? An even split, right? So if I want to put exactly half the elements over here, exactly half the elements over here, and put the pivot right in the middle, what should I be selecting? No. The thing that's in the middle is called I think you said it, the median, right? If I always selected the median, then this behavior here would be guaranteed. Great. How do you select the median?
You gotta sort it.
Sort it. Sort it and then just jump to the middle, right? So putting the cart before the horse. That's the easiest and best way of finding median finding. Sort it and then just jump to the middle. There is a median finding algorithm that works in linear time. That works in linear time. It's very complex. It's not worth it in practice at all because it requires yet another recursion. Right? So don't worry about it. Right? But it is possible to achieve this theoretical best case scenario. Right?
Why? Why does that exist?
The median finding algorithm?
Yeah.
Because it's of theoretical interest, right? You can, computer science theory is all about what can you do, what can't you do, right? So eventually you'll get into things that are called like NP completeness. These are the hard problems. For example, finding what's called a Hamiltonian cycle in a graph, a cycle that visits every vertex exactly once, right? Given a graph, does it have a Hamiltonian cycle or not, right? That's an NP complete problem, meaning that nobody knows how to do that efficiently at all, right? And is it even possible to do it efficiently, right? That's a huge open theoretical question. We don't know, right? Can you do it? Can you do it? Yes, given an exponential amount of time you can. Can you do it in polynomial time with like a linear algorithm? Probably not, but we can't say for sure. Right? Encryption, given a very large number, can you factor it quickly? Right? Nobody knows how. If somebody figures out how, that breaks encryption. Right? Yep. It breaks public key cryptography. Not there's still a lot of encryption. It's just that it would set up a world in which you had to go to Amazon and exchange some electronic keys, and then go back home and start shopping, and then you would have secure communication. You couldn't just say, "Greetings, greetings. Let's exchange some stuff secretly without ever having met before in our lives." Right? And integer factorization and discrete log problem are two problems that all of that encryption is based on. Yeah.
That's what they use quantum computers for.
Quantum computing can break both of those problems.
No, they use quantum computers to have a safe encryption that is
Oh.
and up to date. And
There is quantum encryption, but that's more based on less mathematics and more quantum mechanics.
yeah, quantum.
Like the second that you observe it, it gets destroyed. The quantum state gets destroyed.
If it's like in the chain, it's like you can see that it's like bad, even though you never share anything.
Yeah, I mean it's like a laser beam communication. That you can you intercept that communication right in the middle? If you do, you interrupt the laser. Everybody will know immediately, right? Stuff like that. Yes. So quantum. We're many years away from that though.
Spend so much time questioning whether something should be done, and you have to ask ourselves whether it should be done.
Exactly. Come on.
That's a
All right, there we go. All right, so one last algorithm that I want to revisit, or actually not revisit, but it might be new to you, is merge sort. Merge sort takes a different approach, a different tactic, a strategy. Whereas with quicksort, we partition it around this pivot element and then recurse, and cross our fingers and hope that the recursion is best case scenario where we've divided it in half. Merge sort guarantees that best case scenario by doing the recursion first, and then on the way back up from the recursion, that's when it does its non-recursive work to merge things together. So here's the idea. In fact, what were the numbers I used before? It doesn't matter. I'll make up new numbers. It's really hard to write random numbers, isn't it? There we go. Okay. 8 numbers. This is all one big giant array. Merge sort starts by doing the recursion in a guaranteed fashion, meaning that we're going to cut this exactly in half. This side gets 2, 8, 4, and 7 as an independent array, and this side gets 1, 9, 3, and 10. Okay? There's nothing to stop us from going further. Let's go ahead and divide this further into 2, 8, 4, and 7. And let's go one more step into 2, 8, 4, and 7, so that everything is an array of size 1, and I won't do the right-hand side. What can you say about an array of size 1? By definition, it's sorted, right? So now let's go back up in our recursion, right? What I'm going to do is I'm going to fast forward. I'm going to fast forward all the way up to, we've already sorted this half and we've already sorted this half. We just need to merge them together. So that's 2, 4, 7, 8. 2, 4, 7, and 8. And what was the other one? 1, 3, 9, and 10. Now what we need to do is we need to zipper these things together. We need to merge them into one sorted array. Like with quicksort, I'm going to establish 2 index variables here. And then I'm going to build a brand new array, putting things where they belong. So I'm looking at 2 and 1 right now. Which one would go first? 1. So I copy it over. 1. And I advance j. Now I'm looking at 2 and 3. Which one goes next? The one from the first partition. I'll name these A and B. Right? And I gets advanced. Right? Now I'm looking at 4 and 3. I take 3 and I advance j. Right? oh, sorry, this is I over here. Right. Now I'm looking at 4 and 9. 4 and I gets advanced. 7 and 9. 7. We're not always going to go left, right, left, right, left, right. So that's just the nature of it. In fact, at the end of this algorithm, 7 gets copied over, 8 gets copied over, and now I has fallen off the edge of its world, right? Do I need to make any more comparisons? No, what do? I just take the rest of these and copy them over, okay? That's the idea. Do we want to write pseudocode for the this merge operation that I just described? Yes, no, we did in the last section if you want to watch the video instead. No? Okay.
Can we skim what you did
I don't know.
last time?
I don't know if it's if it's possible to skim, but okay, we'll try it like this. Actually, here's a skim. I'm going to need a bunch of index variables, I, j, and k. I'm going to start them all at 1. Right? Pseudocode, right? I just made up a new rule. You can assign the same value to multiple variables. Right? Cool. You can do that in Python, by the way. Does anybody do Python stuff? All right, so you can do a tuple, I, j, k equals 1, 1, 1. Oh, okay. But unfortunately, they're stuck in a tuple now. No. If you gave them names, then you can pull them out of the tuple too. Right? Yay. So while my 2 index variables have not fallen off the edge of their worlds, right? What I'm going to do is I'm going to assume that A has values A1 through N, and B has values B1 through Bm. Just so that I have 2 different variable names here. Okay. So while I is still processing A, and J is still processing B, I will continue. All I need to do is I've got now I and J. Whichever one is less, that's what I put into C. So if A sub I is less than B sub J, then A sub I is what needs to go next. C sub K will take on the value A sub I. Else, if A sub I is greater than or equal to B sub J, then C sub K will take on the value B sub J. You don't need that else if there, right? So this can be thrown away because it's one or the other. I will increment K. Oh, and if I advance, if I take A, then I will need to increment I. If I advance B, then I will need to increment J. Right? That's all there is to it. Except for when you get when one of them falls off the edge of the earth, off the edge of their world, I need to make sure that I copy the rest of it. So that's just 2 more while loops. While I is less than or equal to N, C sub K is A sub I plus plus, K plus plus. And then independently, another while loop for the, in case it's the other one, C sub K is B sub J, K, J plus plus, and K plus plus. Right. All 3 of these loops are independent right after the other. They're not nested. Okay. This is the merge operation. Right. Having seen this, how many comparisons do you end up making? In the worst case. Take this one, then this one, 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 this one. It's completely zippered up, right? How many comparisons did you make if there are, say, n divided by 2 elements over here and n divided by 2 elements over here so that you have n elements in the resulting array? N, or thereabouts. N minus 1 technically, because you're going to have at least one last odd man out at the end, right? So the merge operation takes n minus 1 comparisons. Right? And since we're doing the recursion to start with, C sub n is there's a perfect recursion here of n divided by 2, but remember that we do 2 recursive calls. There is a non-recursive cost of n minus 1 comparisons. Look familiar? It's already what we did. N log n. Right? Lots of smart code here. Right? No data structures at all except for an array. It's going to be very well contrasted with what we're going to be doing by the end of the semester in 2 weeks, where smart data structures and dumb code are a lot better than the other way around. Right? Right? That's pretty dang clever code there, right? At least my opinion. I didn't make it. I just remember it off the top of my head. So, yeah. Right. Any questions on algorithms, algorithm analysis, searching, sorting, etc.? Yeah, go ahead.
I didn't understand the part why the worst case is n minus 1 and merge sort again.
Okay. Oh, here, let's start over. So suppose I've got 1, 7, 3, 2, 4, 8, 9. Okay? So this is my pivot element. I start I and J. Right? This is on the wrong side, right? It needs to go to the right.
Oh, that is quick sort.
Oh, sorry. Merge sort. There is no best, average, or worst. It's all the same.
Oh, so when you plus n minus 1.
This is the merge operation. Right? So graphically, what I'm doing here is I'm doing a divide and conquer. Right? I'm making 2 recursive calls. If I started out with n, then this one gets n divided by 2, this one gets n divided by 2. Right? Dot, dot, dot. When I come back up from the recursion, I have an n divided by 2 and an n divided by 2 array that I have to merge together to create a new array. Right? So I've got the recursion, 2 recursive calls on sets of size 1/2. But then when I come back from the recursion, I have to pay to merge them together. And then send them on back up the chain of recursive calls. Yeah?
So depending on like what operations are like most expensive for me and then like what types of arrays I have, I will choose which sort.
Yeah, that's an engineering question at that point. In which case you'd have to set up proper experiments like you kind of did in your, we did for you in your lab, right? Where you run it on a whole bunch of different test beds and okay, well, and tune it out and tune it. And I don't have my Eclipse open here, but Java 7 and prior used a hybrid of merge sort and insertion sort. So you can go with hybrid algorithms too, where merge sort is guaranteed to be fast. But at some point, you, from a practical perspective, you start paying more for the recursion. It doesn't break it all the way down to an array of size 1, right? That would be insane. Instead, it stops, and I think that the original was it stops at arrays of size 20. And then it switches over and just does a really quick insertion sort on an array of size 20. Because that, from a practical perspective, that order n squared algorithm was faster on small arrays than on larger arrays, than merge sort.
Right formula where those two.
And that crossover point, yes, that's where your experimentation comes in. And I don't know how they got 20 at one point. They just ran a bunch of experiments, said, yeah, that's good enough, 20.
Is there like a way to kind of like right now we're doing it from mathematical approach where we like basically count it up. Is there a way to like make a bunch of tests and see how it progresses up?
You could, yeah. That's what I did originally with this experiment. Go, iCloud. If you remember this graph that I showed you, where is it? Nope. Yes, this one. Right? That's how I generated this. Right? I just ran it over and over again for various lists of certain size. The blue, I plotted that, and then I did a quadratic interpolation to get the nice smooth red curve there. Right? Yeah, you could do that. If you're benchmarking various implementations, then yeah, you can find that stuff all over the place. Right? You generally don't want to set your own up when there are a bunch out there already to do it for you. But yeah.
I was wondering, how do we, the thing I was having the most trouble with, was choosing like what's our main operation. and
Okay.
How that works. It's like, once you have that, like I guess I'd be okay.
Okay.
with master.
I mean, there's no one right answer for what your elementary operation should be for every algorithm. For example, with merge sort here, darn it.
Right, it's
For-
more just like, what to ignore and what to.
If it's necessary for the control structure of your algorithm, you ignore it. If it's only done once, ignore it. Restrict your attention to things that depend on the input size and will grow with the input size, because you don't want to give the misimpression that it's an order 1 algorithm, right? With merge sort here, you could say, well, memory is my bottleneck here. And the way that I presented it here was not in place. In other words, if you're going to merge 2 arrays, you need to create a brand new array. You're taking double the amount. Or you need to reuse that array over and over again. Right? So it takes roughly order n additional memory. Whereas quicksort didn't require any additional memory other than a temporary variable to swap 2 variables across. Right? So if memory is your bottleneck, then pay attention to that. Right?
To pay attention to the size, I guess.
The most relevant, the most expensive, the most common operation. That's going to be different things in different situations. Yeah.
How would I count memory stuff if, like, for example, with operation, like when it was done, it's done, but with memory, it's like I took some memory and fixed some memory, took it, and then it's really.
Well, if I'm doing this as an actual implementation, I would only allocate an additional array exactly. If there are 1 million elements, then an array of 1 million, because that's all you're going to need. You can reuse that. And if it were Java, I would put it as a static allocation so that you could reuse it on each iteration of your recursion. Even implementations of like qsort in C, they don't actually use recursion. They simulate recursion by creating a chunk of memory and then reusing it over and over.
So for this one, it would be like memory equals to n?
Order n, right?
Yeah, or
Just a linear amount of additional memory, yeah. Double the amount. And then, of course, you might copy it to 1 and then copy it back. So order 4n copies or assignment operations, the 4 goes away and it's still order n operations on that. But comparisons are, you do order n log n of them, so that's more. Right? Okay, so the next topic that we're going to go over is our trees, right? And trees are data structures that, I'll just give you a preview here of what a tree might look like. This is going to be a binary tree, binary search tree is ultimately what we're going to be looking at. So let me take those other elements. Oh, that's too far gone. Let's go ahead and just make up new elements here. 10. Let's go, no, I want something larger. 40. There we go. 20. There we go. 15, 17, 3, 30, and 35. And then something over here, 50, 45, and I don't know, 70. Right?
Is this something similar like in 235?
C diagrams? What are C diagrams?
SE diagram.
Oh, Hass diagrams. Oh.
Yeah, has yeah. That's basically what
So,
it's
I mean, you've stumbled upon a universal truth. Everything's a graph.
like. Wow.
ER diagrams, UML diagrams, binary search trees, Hass diagrams, right? Chemical chemical compounds, right? Everything's a graph. That's why it's so important to have some graph theory. All right. This is a special type of graph. It is a tree, which makes it an acyclic graph. It is an oriented tree. It goes top to bottom, right? Unlike natural trees, they grow up. All of our trees grow down. Right? And there's a very good reason why. It's because they hold data. And we read data left to right, top to bottom, right? So that's why our trees grow down. Not only that, but it is oriented left to right, right? Kind of like a family tree. Family trees grow down. You've got ancestors and descendants. In fact, we use the same terms here. We've got parents and we've got children. Right? Not only that, but we have additional structure. Every parent has at most 2 children. Right? You can see here that some nodes don't have any children. Right? I shared a nice acronym today in the main class. You may not be aware of it. DINKS. Does anybody know what a DINK is? Yep, double income, no kids. Right? So we've got our DINKs down here. These are called leaves. Why are they called leaves? What are the things at the end of the trees? They're leaves. Right? These are branches, right? Branches grow outward. Again, they're growing downward. We've got parents and we've got children. We've got a left child and a right child. Some things have a right child and no left, some things have a right child but no left child. Some things have a right child, and I don't have an example here, but I can add another one. I can, like 90 here. That's exactly the same as before. Over here, what would I have to do there? Greater than 65 would work, right? So, some things have a left child, but no right child. Some things, again, have no children at all. Some things have both children. That's called a binary tree. And at the very last, we have key values in the binary tree. In this case, I'm just using integers. Make an observation about all the values over here with respect to 40 and all the values over here with respect to 40. Everything over here is less than 40. Everything over here is greater than 40. We've seen now multiple instances in which we can exploit this kind of structure. Binary search. Jump to the middle. It's either there or it's left or right. Partitioning. If you choose the optimal element, put everything over onto the left, put everything onto the right. That's where it needs to be. Right? Merge sort, not really, but. So how can you exploit this structure? I want to search for 30. You start at what's called, well, in a tree, where do you start a tree? A seed, but what's at the leaves are up there and we've got branches down here. What's at the bottom? A root, right? You start at the root, and I see 40 here. If you wanted to search for 30, where would you go? The left. Effectively cutting out half the tree from consideration, as long as it's a balanced tree, right? What's it called when you cut a branch off a tree? Pruning, right? Trimming, right? So now I go down here. I'm searching for 30. You can make the exact same observation as before. Everything over here is less than or equal to 20. Everything over here is greater than 20. So where would you go? To the right. Right? And you find it right here. How many comparisons did I need to do that? 1, 2, 3 to find what I was looking for. Right? Rather than the 4, 5, 6, 7, 8, 9, 10, 11 things that are in there. Right? Yeah. Yeah. You can travel up the tree, you can travel down the tree. Another question? Backtracking, like algorithmic backtracking, it can be visualized as a tree, in which case you travel back up. That branch didn't work. Let's go back up and try a different branch. Certainly traversing a tree, and we'll get into tree traversal algorithms as well. I wanted to give this to you as a preview of what we're ultimately going to do, binary search trees in the end. But how did we get there? Right? I fast forwarded through all of the steps to get there. That we start out with general graphs and everything is a graph, right? Then we said, no, we want acyclic graphs. We added structure to it. Then we said, we're going to put data into our acyclic graph, which is now a tree. So we're going to orient it, right? Top to bottom, left to right. We're going to add more structure by limiting the number of children that you can have from to at most 2. Right? Then we put even more structure on it. You can see it, my hands here going from general. I'm squeezing it down. Right? We put more structure on it by saying that the keys, everything down there is less, everything down there is greater, until we can finally restrict it all the way down to something that we can now exploit for fast operations. Right? No structure. More structure, more structure, more structure, more structure, highly structured, right? Why do we want that? What is this course about? A little bit about data structures. Structure is what you can exploit, right? Just like if you have an array, what structure do you want to exploit? You want it sorted so that you can exploit binary search for fast operations. Right? This is, by the way, another way that you can look at binary search trees is as the best of both worlds of linked lists and arrays. You don't have random access of like arrays, but also you don't need to. You also have the linkages, the advantages of linkages with a linked list. Except that instead of A goes to B goes to C in one long chain, you break that chain up so that you can have branches now. So you can imagine also how you would implement this. Node doesn't just have next. It has left child, right child, and optionally a parent. Right? So it has 3 references to other things. More linkages means that you can get more out of it. Right? Not really. You just have to find where it needs to be and then splice it in. So I don't think any of us are arborists or whatever they're called, but one way that you can grow a tree is through grafting, right? All you do is you cut a little bit out of it, you take a branch of a completely different species in some cases, and put it on there, tie it together, and it'll grow. So you can grow oranges out of a peach tree. I don't know if that's possible or not, but I'm not an arborist. But that's where we'll go on Tuesday.